In previous class, we have discussed about electrode potential and standard electrode potential. Now we are going to discuss the mechanism how electrode potential is generated at the surface of electrode and its electrolytic solution. In electrode potential, one electrode is immersed in its electrolytic solution. An electrode is a metal, or sometimes it may be gas also. And therefore, before discussing the mechanism, we have to know what is matter. The constituent of solid metals are positively charged metal ions and mobile electrons. There is like solid sodium chloride is an ionic solid. In sodium chloride ionic solid, constituent particles are sodium ions and chloride ions. And these ions are held together by strong electrostatic forces of attraction. In metals, according to electron C model, the metal has two parts. One is positively charged metal ions part, another is mobile electrons. According to electron C model, positively charged metal ions are in sea of electrons. As in figure, these are the metal ions, positively charged metal ions, and these are mobile electrons. They are moving like this way. If one electron moves, then this vacancy is filled up by the nearest electron, and like this way electron moves. And this is the constituents of metal solid. You may think that metal elements like iron, zinc, copper, and constituents are metal atoms. But here metals atoms not exist as a neutral form. These metal atoms lose their electrons and become positively charged, and whatever lose electrons, they are in crystal lattice and have these ions by electrostatic forces of attraction, and these forces of attraction is also known as metal bond. And under high pressure, when we make metal rod or metal wires, the electrons and positively charged ions are regularly arranged. Say this is a metal rod, a copper rod or a zinc rod, anything. These electrons and positively charged metal ions are regularly arranged. And this is one of the properties of metal. That is, metal has two parts. One is mobile electrons part, another positively charged metal ions part, and they are regularly arranged. And electrons are mobile. They move. They can carry electricity. Now, when this metal state immersed in electrolytic solution, then two types of forces arises. That is, one is solution pressure, another is osmotic pressure. One is solution pressure and another is osmotic pressure. Solution pressure, tendency of metallic element and hydrogen have a tendency to pass into solution in the form of positive ions. This property of metal is called solution pressure or electrolytic solution pressure. Here metal solid is converted into metal ion with elimination of electrons. So again see, the tendency of metallic elements and hydrogen have a tendency to pass into solution in the form of positive ions. This property of metal is called solution pressure or electrolytic solution pressure. That is, when we immerse one metal rod in its electrolytic solution, the metal of the solid have a tendency to convert into metal ions, and that tendency is called solution pressure. Then another is osmotic pressure. Tendency of metal ions to convert metal and deposit it on the electrode. This is called osmotic pressure of ions in solution. This is the reverse process. Osmotic pressure, this is tendency of metal ions to convert into metals and deposit it at the electrode. That is, metal ions accept electrons and converted into metal solid and deposited at the electrode. This is two factors which govern electrode potential. There is one solution pressure, another is osmotic pressure. So again see, we have defined what is metal, what are the constituents of metals, solid metal. Another solution pressure and osmotic pressure. In solution pressure, that means metal solid has tendency to convert into metal ions, and osmotic pressure, the tendency of ions to convert metal and deposit it on the electrode. This is called osmotic pressure of ions. Now let us discuss how solution pressure and osmotic pressure play role to formation of electrical potential at the surface of electrode and electrolytic solution. There are three cases arises. Number one, that is when solution pressure is greater than osmotic pressure. If solution pressure is greater than osmotic pressure, the metal electrode lose electrons, and whatever electrons lose, they left at the electrode, and ions are migrate towards the solution. The ions migrate towards the solution, electron left at the electrode. Therefore, the electrode becomes negatively charged. Since zinc ions migrate towards the electrolytic solution, therefore concentration of zinc to positive ions increases in solution. And the reaction is that zinc solid is converted into zinc to positive ions and migrate towards the aqueous solution, and whatever electrons left, they are present at the electrode. And concentration of zinc to positive ions increases at the electrode with respect to what? Sulfur ions. See, these electrode, zinc electrode now negatively charged, therefore whatever negative ions present or negative charge present in electrolytic solution, in this case sulfur ions, and positively charged ions are zinc positive ions. Since electron is negatively charged, therefore zinc positive ions get accumulated at the surface of the electron. Hence, a electrical layer is formed or charge separation takes place at the interface of electrode and electrolytic solution. You can see that when the metal electrode undergoes oxidation, the metal is converted into metal ions and migrate towards the electrolytic solution, and left electrons at the electrode is negatively charged. When this electrode is negatively charged, then whatever positive ions present in electrolytic solution that get accumulated at the surface of metal electrode. And when these positive ions accumulated at the surface of the electrode, an electrical layer is developed. Due to formation of this electrical layer or charge separation, a electrical potential is developed. Electrical potential is developed, and that is called electrode potential. Now you understand how electrode potential is developed. Say, there are three cases I have already told. Out of these, in the first case, when solution pressure greater than osmotic pressure. Solution pressure is the property of metal. It loses electrons and becomes positively charged when the electron emerges in its electrolytic solution. When this electron undergoes oxidation, they lose their electrons. These electrons left at the electrode, therefore this electrode is negatively charged. As soon as this electrode is negatively charged, positive ions, whatever present in electrolytic solution, that get accumulated at the surface. Therefore, one charge separation takes place at the junction of solid and liquid interface. As such separation takes place, a potential difference is developed, and that potential difference is called electrode potential. In this case, zinc undergoes oxidation, therefore it is called oxidation electrode potential. Now, after formation of this layer, electrical layer, oxidation of zinc solid slow down. The conversion of solid metal to metal ions, the process becomes slow down and backward reaction is started. Now reaction will be reversed. This reaction, say in the first case, zinc lose electrons and become positively charged, left electron at the electrode, and these ions migrate towards the solution. Now what happens when this layer formed at the interface? This interface is not allowed to transfer these electrons, to transfer these zinc ions towards the solution. Therefore, a reverse reaction takes place. That is, zinc ions now accept electrons and convert it into zinc solid. So again, I like to discuss that when this electron is negatively charged, that is more electrons present. After some time, it when electrons are moved, then electron-electron repulsion also takes place. Electron-electron repulsion also takes place. Therefore, these electrons accepted, that is reverse reaction. These electrons now accepted by zinc 2 positive ions, that is this reverse reaction. The reaction will be reversed now. But the reverse reaction is slow with comparison to the forward reaction. But at the electron, a reversible reaction takes place. There is zinc solid is converted into positive ions plus twice electrons, and the process is reversible, and after some time the equilibrium will be exist there, and then the electron reaction is reversible. It is here forward reaction is fast, but backward reaction is slow. Therefore, whatever electrodepotential will get, that is called oxidation electrodepotential for zinc electron, and it is dependent upon the nature of metal which undergoes oxidation, and it is not all metals undergoes oxidation. Those metal undergoes oxidation, which metal undergoes oxidation, that will be dependent upon nature of the metal. And another case, that is when solution pressure is less than osmotic pressure. This is another case. Solution pressure is less than osmotic pressure. Already we have discussed that. If solution pressure and osmotic pressure, if osmotic pressure is greater than solution pressure, or solution pressure is less than osmotic pressure, then this is the property. The osmotic pressure is the property of the metal ions to convert into metal. In this case, say we are taking example copper electrode in copper electrolytic solution. This copper 2 positive ions from the solution accept electrons from the electrode and convert it into copper solid. As copper 2 positive ions accept electrons from the electrode, the concentration of copper 2 positive ions decreases in solution and concentration of sulfur ions increases. As that is, these two copper positive ions now accept electrons from the electrodes and convert it into copper solid. And these, I like to mention that whatever these electrons are present at the electrode, they are present in the conduction band, that is non-bonding molecular orbitals of the metals, that we'll discuss. You will get in NCERT the solid state chapter, conduction band, valence band, and it is band theory of conductor. The metals are good conductor, and from metals, the property of metals, the conductivity properties can be explained with the help of band theory. And these electrons are present, that is loosely, that is this mobile electron can easily taken by the copper 2 positive ions whatever present in the solution, and as number of electrons that is decreases in the metals, therefore these electrons now positively charged. The electron is now become positively charged. As this electron is positively charged, whatever the negative ions present at the electron get accumulated at the surface, and from a electrical layer or charge separation, due to this charge separation, a potential difference is developed, and that is called, in case of copper, it is called copper electron potential. Now, the electron reaction is that copper 2 positive ions accept 2 electrons and convert it into copper solid. And this reaction also reversible. That is, after some time, this copper 2 positive accept electrons That is, first, this copper to positive ions accepted by the copper and converted into copper solid. After some times, this copper solid can lose electrons and becomes copper to positive ions. That is, the reverse reaction takes place. Because after formation of this layer, the transfer of ions and transfer of electrons now slow down and reverse reactions slowly taking place, and therefore this electrode reaction also reversible. But in this case, forward reaction is faster than slow than the reverse reaction. Therefore, this electrode potential is called reduction electrode potential. Now you understand how electrode potential is developed at the surface of electrode. That is, the metals, when immersed in its electrolytic solution, then at the interface a electrical layer is formed, and the formation is different types. Here we have discussed two types and how these potential difference develop, that is dependent upon solution pressure and osmotic pressure. Now third case, that is what happens when solution pressure becomes equal to osmotic pressure. Then if solution pressure is equal to osmotic pressure, no transfer of ions and electrons takes place at the surface of the electrode and electrolytic solution. In that case, we say that type of electrode as null electrode, and equal as null electrode. There is no electrode potential takes place if solution pressure is equal to osmotic pressure, and that type of electrode is called null electrode. Here two types of electrode potential we have seen. One is oxidation electrode potential, another is reduction electrode potential. That is, when an electrode placed in electrolytic solution, two types of reactions possible. One is oxidation and another is reduction. The magnitude of oxidation and reduction potential is equal but sign is opposite. For example, zinc, in case of zinc, oxidation potential of zinc is plus 0.76 volt, but reduction potential is minus 0.76 volt. Similarly, reduction potential of copper electrode is 0.34 volt, but oxidation potential is minus 0.34 volt. In previous class, we have discussed that absolute value of electrode potential it is not possible to determine. So whatever potential difference is developed, that potential difference has a value, that absolute value, that is absolute electrode potential, it is not possible to determine. It can be determined by comparing the potential difference with the standard hydrogen electrode. That is, by taking standard hydrogen electrodes as a reference. In our next class, we'll discuss about standard hydrogen electrode and what is the standard hydrogen electrode potential and how can we determine electrode potential of an electrode with the help of standard hydrogen electrode. And in today's class we have discussed how electrode potential is developed when an electron is immersed in its electrolytic solution. There many questions arises from today's discussion. Out of that, one question is that why in zinc electrodes, we use, that is, zinc electrodes when we use for the setup of any galvanic cell, or copper electrode is used for setup of any galvanic cell, as for example linear cell. Why we keep out the zinc electrode from the solution? Why we keep out the copper electrode from the copper electrolytic solution after use? And why we will not get the electrode potential if we place an electrode in other electrolytic solution? Why would we place the electrode in its electrolytic solution, not other electrolytic solution? If we place the different electrode in other electrolytic solution, what will happen? And that type of question arises, and you try to think, answer this question. The why potential difference, what will happen if we place zinc electrode in copper sulfate solution, or copper electrode in zinc sulfate solution, what will happen? And you try to think and try to answer this